So whenever, so I'll start here.
Okay.
Ready to go?
Yeah.
All right, this is another very professional video we're doing here. Okay, so this is the possibility if we have a snow day. If we don't have a snow day, this video will still be useful to you. If for whatever reason we have a delay or a cancellation on Wednesday, so some things you can do. So today in class, we obviously did a lot of material. The bottom line is you should now be able to do homework problems 1 through 8 on the week 2 assignments. The first 3 problems are something I ask you to kind of do on your own. E equals h nu, E equals hc over lambda, kind of doing the basic calculations associated with light and understanding light and energy and frequency and wavelength. So do those to the best of your ability. So those are the first 3. The other, I guess that would be 4 through 8 are related to isomers that we did in class today. So if you need more time there, great. Obviously watch this video. If you need to review your quiz, great. And if you have any problems from last week that we didn't get to, finish those up. And then Friday's quiz, as I mentioned, will be kind of a basic question about complex ions. So none of the material that I'm about to do. Okay, so what are we doing? And just let me know if I need to slow down. Okay, the thing we haven't discussed is, in a sense, why do we care about metal ion complexes? Well, they have interesting properties, and they have interesting properties because of the d orbitals that are present in transition metals. So I'm going to spend a little bit of time reminding you a little bit about d orbitals. You already know there's 5. You put 5 boxes, and you put 1 electron in each. And I don't know if you can see this, but you might also remember from first semester Gen Chem, you have 5 different types of d orbitals. They're all at the same energy level, so they're called degenerate orbitals. They're all at the same energy level. We have a dxy, a dxz, a dyz, a dx squared y squared, and a dz squared. In first semester, we didn't really care that much about those, okay? We kind of treated them all the same. The thing that's interesting to note is that the xy, the xz, and the yz, those lie between the xy axis, the xz axis, the yz axis, and the x squared, y squared, and dz squared lie directly on those axes. That's a really important distinction to make for what we're about to do, okay? Because these orbitals don't stay degenerate in transition metal complexes. They actually split into sublevels based on the geometry. And that's what I'm going to show you right now, strictly for octahedral geometry. We'll do 2 other geometries, but the video will be way too long if I do all of that. Okay, so 3-dimensional space. These lie between the axes. I'm going to try to draw these. So I've got 5 x, y, z coordinates. Now I split them up into 2 sets, but this is not splitting into different energies. I'm just showing the geometry here, okay? So it's not like these are higher energy, these are lower for now. I'm just going to show the shape. So dyz, I've got to look at my notes, or excuse me, dxy, they lie between the x and the y axis. So one of those lobes is actually on the z axis, and the other lobe is in between the x and the y. So it's not on the x or on the y, it's in between. Well, if it's going to be between the other way, it has to be on the z axis. So that's the dxy. The dxz, well, one of them is going to be on the y, and this is hard to draw. Between the x and the z, it's kind of a pain to draw. So we draw it here, and we draw it here. I'm not very good artistically at this, so you could probably do a better job. And then the dyz, the dx squared y squared is on the x and y z axis, so that's easy. It's on the x and it's on the y. And you might recall that the dz squared has a rather odd shape. So it has one lobe that's on the z axis, and then it has this other region of electron density kind of going around in a donut shape, which we kind of shade in. Okay, it's not important that you really know the shapes, okay? What's important to know is on the axes, between the axes. That's very important for, now essentially here's the whole idea. Okay? When ligands bond to the central atom, a ligand has negative charge, and when a ligand approaches these orbitals, they affect them differently. They will repel negative charges. All these things are negative charges. They will repel these electrons in these orbitals differently and split the d orbitals into sublevels, depending on the geometry. Octahedral, tetrahedral, square planar, trigonal bipyramidal. We're just going to look at octahedral today. Okay. So, great, we know what those look like, and so what do octahedral ligands, or ligands in an octahedral complex, do? Okay, so we're going to call this d-orbital splitting, so being separated into sublevels in octahedral complexes. We'll do other shapes, I'm just going to do the one now. So if it's octahedral, instead of doing above and below the dashes and the wedges, I'm going to put them on these geometric planes. But it's the same thing. Here's your square planar. So we have a ligand and a ligand and a ligand, a ligand, a ligand, and a ligand. It's just a different way of representing an octahedral using an X, Y, and Z axis. Okay? Now, so there's a ligand on the x-axis, the y-axis, and the z-axis, and since the axes have two different points, they have a ligand at each end. Here's where you're just going to need to listen and kind of help and see if you can follow along. Okay? So I'm making the argument that these 5 orbitals are no longer the same energy level when ligands approach them. So here's the basic idea, okay? Let's see. So you've got ligands on the x-axis, on the y-axis, and on the z-axis. See why I keep saying on and between, okay? So when you have the ones that are on the axis, I said look at my notes. I think I can do it without my notes now. So you've got this one and this one. Here and here. Where this electron density, remember that's what these shapes are, they're electrons. They're these clouds of negative charge. So you've got them on the y-axis, on the x-axis, and on the z-axis. These two are going to be repelled more when the ligands approach them. What does that mean? That means that these two are going to get pushed to a higher energy level. Than the other ones. This is hugely important, okay, to understand transition metals. So what we have is a splitting of these 5 orbitals into 2 sublevels, 3 and 2. There's a couple things I need to label here, okay? Now I'm not going to get too hung up on this. There's some nomenclature here. This level, the ones that go to the higher level, are called the E sub G orbitals. That's really just vocabulary. I'm not too worried about that. The lower energy level orbitals are called the T, that's a T, sub 2G orbitals. Again, don't get hung up on that. The idea is these are down here, these are up here, and you have this split in energy. And we use the symbol delta all the time to indicate a change, a difference between this energy level and this energy level. In this case, this is the difference in energy for an octahedral complex. Okay. Now I think I'm going to probably stop there. Okay, because there's some additional information. This whole theory that we're discussing here is called crystal field theory. It's how the electric fields of ligands and orbitals interact with each other. And in octahedral complexes, they split into 2 and 3. In other complexes, it's going to be the exact opposite. In other complexes, it's actually going to split up into more than 2. And now, the other thing, which I'm not going to go into here because the video is getting too long, is how big this energy is, how big this gap. Is it a small gap? Is it a big gap? It all depends on what these ligands are. And just to let you know, how do you know that? On the back of this table, which I'll mention in class, okay? The ligands at the top, which are called strong field ligands, make a big gap. The ones at the bottom, I think, oops, I said that the exact opposite. The ones at the top are what are called weak field ligands, small gap. The ones at the bottom are strong field ligands, and they make a much, much larger gap. Once we get that, then we have to refill the electrons into these orbitals like we did before. So we put them into the boxes one at a time, and how we do it depends on if it's a small gap, we put one in each box. If it's a big gap, we fill this level first before going to this level. That's a lot, okay? That's octahedral, the other ones, and that's the most important. So if we can get the concept down here, then we'll actually do some problems in class. Thank you.